see the spectral rescale, so how to make rescale for the image. Then we will see how to apply some geometric transformation like rotation, translation, shearing, etc. Then we'll see how to apply some filters for the image. Sometimes you have an image that is not clear. For example, we can make this image more clear. So we can sharpen, for example, the image, or we can make a fade image. Okay. And then we'll see how to make the color conversion, how to convert, for example, from colored image to grayscale image, etc. And then finally, we'll see the lookup table, so how to edit the pixels of the image pixel per pixel. Okay. Now, first of all, what is an image? So I've seen that I already explained that you have many types of image. So we can have the binary image. So in the binary image, what do you have for every pixel here? In the pixels, for the image, what do you have? We have rows and columns. And the image is nothing but a set of pixels. So the pixel is the smallest element. So this is the pixel. Now, how can we write this pixel in the computer? So here, if it is, for example, black and white image. So here we'll have two values, 0 or 1, black or white. Okay, in that case, for every pixel here, we can write the value 0 or 1. That case we call binary image. So it can be black or white image. The second type of images that you can have is the grayscale image. So what does mean grayscale? For every pixel here, we have a range of gray. So we can have values for every pixel from 0 to 255. So the 255 here is the white, and the 0 is the black. So as an example of grayscale image, we can have the medical images. So the X-ray image, the MRI image, CT scan images. So all these images, they are grayscale image. Okay. So the image here is nothing but a matrix. So you can say that you have this image. In this image, we have rows and columns. And then here, the smallest element is the pixel. And for the pixel, we can have any value from 0 till 255. So to create a value or to write value from 0 till 255. So you can see that here we are using 8 bits. This is called 8-bit image. So we are using 8 bits to write every pixel. Now you can see that the first pixel is white. You can see that the value is 255. This pixel is white, same thing, 255, etc. Now this pixel here, what do we have? We have here, for example, 20. So 20 is something that is near to the 0. So here, this is the white, and this is the black. So the 0 here and 255. So if you have something that is clear to the 0, it will be something, it will be gray, but it is dark gray. So here we'll find light gray that is clear, that is near to the white. Okay. Now here we can see that you have the value 20. So 20 is almost black. So here you have pure black. So we can see that you have the value is 0. And here you have some gray. You can see that here you have, for example, 75, then 75. So here we can have any value between 0 and 255. Any question about this? So this is called grayscale image. What is the next type of image?
Binary.
Okay, we have seen the binary already. This is the grayscale image. And what is the next type of image? We have seen this together, and you have seen this also in other courses. So the next type is the color image. Color image. So here we are using the RGB image. So RGB image, we have for every pixel, we have a value from 0 to 255. And here we are not talking about just one color, but here for every pixel, here we can have 3 components: the red, the green, and the blue. So the red here will be any value from 0 to 255. The green will be any value from 0 to 255, and the blue will be any value from 0 to 255. So in that case, we will not have one matrix, but we'll find 3 matrices. So the matrix will be here multiplied by 3. We'll have one matrix for the red, one matrix for the green, and another matrix for the blue. Okay, for the first pixel here, so if you have 255 for the red, if you have 255 for the green, 255 for the blue, so this will give us the white color, etc. So if you have, for example, here 255 for the red, 0 for the green, 0 for the blue, this will give us the pure red, etc. Okay, so here we have an example. So here we have an example of matrix, and this matrix is the matrix of grayscale image. Now, what is image processing? So each pixel here represents a color, gray level, or another attribute. It can be a binary value, black or white. So here color, we are talking about the RGB color space. Gray level here, we are talking about the grayscale color space, and we can have also binary image. So the image are useful object in graphic rendering. The output of graphic rendering is typically an image. So if you have any graphic, you make the rendering, you find an image. Okay. And here we have some pre-processing facilities like the rescaling. So we'll see what does mean rescaling. We'll see how to make some filtering and how to make some geometric transformations. So rescaling here, we are talking about how to change the colors of the image to make it a darker image or lighter image. So we can add some light to the image, or we can remove some light to the image. Okay. So here the next type will be filtering. We'll see how to apply some filters, how to create filters. So the filter is here, we are talking about the kernel. Generally here we are talking about the matrix. It can be 3x3 matrix, it can be 5x5 matrix, 7x7 matrix. And here we are applying, for example, kernel. We are creating kernel. This is an example of kernel here. And if you apply this filter for all the image, for all the pixels of the image, you will find the filtered image. So here we are talking about the convolution product. We have a matrix, which is the image, and we will apply this kernel to every pixel of the image. We will see the details in the next slide, inshallah. And then we see the geometric transformation. So all the geometric transformation that we have seen previously, the shearing, the rotation, translation, etc. All these geometric transformation can be applied to the image. We have seen previously that to use an image, you have to use the buffered image class. Okay, so okay, use, for example, buffered image. You give the name, for example, I. You can initialize it by null, and then you can read, for example, an image. Okay, and then here for the buffered image, it contains both. It contains the raster and it contains the color. So the raster here is nothing but the data. So it represents the pixel values in numerical format. And the color model here specifies the mapping between the numerical values and the raster. So you can have a color model of grayscale. You can have a color model of standard RGB or linear RGB. Okay. And here the raster is here the values of the pixel, and the values of the matrix. Okay. Now here we have the Java Advanced Image, which is an optional package that you can use. It can offer many image processing capabilities. Now, generally, what are we doing in image processing? We have an image file. It is stored here in the computer, or it can be stored in the cloud or in the web. Okay, so here we have an image file. So here it can be, for example, a link here, a link of an image that is stored in the net. Okay, then we can read the image. So we see the method that we can use to read an image, which is image I.read. Okay, and then here we have the image. For this image, you can display this image on screen. You can check or modify the raster of the image. You can print this image, etc. Now, if you want to make image processing, here you can use the different operators. For example, you can make shearing, you can make rescale operation. So here we have many options of image processing. Okay, so we'll see all these tools in this class, inshallah. And then you have the new image. Okay, so after applying the operators, we have here the new image. So this new image, you can write it here as a file. Okay, you'll see the instruction or the method that you can use. So you can use here image input output dot write. So this will write the image, or you can display this image on the screen. Any question about this? So the first part here is just reading an image and displaying an image. You will see the program of this part. Okay. So in today's class, we'll start by doing this. We'll just try to read an image. First of all, we have to create a buffered image, and then we can read an image from a file or from a URL, and then we can display this image. In the second step, we'll see how to apply some operators, how to change the color, how to make the rescale operation, how to make geometric transformation, how to apply some filters, etc. And then we have the new image. So this new image, you can display it on the screen. You can also write it on the computer and save it as a new image. So for the image in Java 2D, here we have the class buffered image. So here we have buffered image bi equals the new buffered image. So this will initialize here an image. Okay, so here we have the dimension of the image, and here we are using an RGB. So this will initialize a buffered image, and it will be a blank image. Blank image, yani the values here will be 0, 0, 0. So if you try to display this image, it will be black image. Okay. And then with the graphics 2D, so object G2, you can perform all the types of graphic rendering, like for example, drawing on the screen. Okay. So first of all, you have to make, you can see that you have graphics 2D G2 equals the graphics 2D. bi.create a graphics. So here we are creating graphics from this buffered image. Here we are using bi for buffered image. Now this is an example on how to create an image. We are creating just an image, and the values will be 0, so it will be a black image. Okay, but before doing this, I prefer to start by knowing how to read an image. Okay. So let's open it. This is beans. Okay. Now this is the program that we can use to read an image that is stored in the computer. Okay. Okay. So first of all, you have to create a buffered image. Okay, so I'm using here the buffered image class. So buffered image, we can give the name IM, and here we're initializing the buffered image by null. And then here we want to read an image from the computer. In that case, we have to use here the file. So I can create a new file. So file f equals a new file, and then here you give the location of your file. Okay. Let's see here. What do I have? An image here. Let's use Parrot 2. And this is the path of the image. Parrot 2s.jpg, and it is stored in the D. Okay. Then I want to read this image. Okay. So to read the image, we have to use image input output.read, and then we are reading from which location? From this location. You can combine these two lines together. You can make IM equals image input output.read of new file, and then you give the location. Okay. So here, when you read the file, this can generate some errors. That's why here we are using here the try catch. Okay, to prevent here generating some errors. Now, once we read the image, you can see that here we have the image is stored in the variable IM, which is a buffered image. Then you can draw this image by using g2.draw image. So here we have the name of the image, which is the buffered image, and then you can give the location where to place this image, and then here the observer can use this or it can use nothing. Okay. Now, when we run this code, you can see that what we did here, we displayed an image. So this image is already stored in the computer. So I have this image. You can open the image from here. You can see the image that we upload. Okay. If you want to use another image, you have to just give the location of this image. Let's use now this image. We'll use this image in the next lections, inshallah. So here we have another image. So what we did, we created a buffered image, and then here we used the image input output.read from this file, and here we can directly make here new file of, and directly make this, okay, and then you can remove this time. So im equals image input output.read, and then we are reading from the new file, and this is the location of the file. Any question about this? So very simple, just 3 lines. Buffered image, you create a buffered image, you read the image, and then if you want to display the image, you can display the image. If you want to store this image, you'll see in the next example how to save an image, and in that case, you have to use image input output dot write, and then you give where to write the file or the format of writing an image, which is here in general to the JPEG, and then the path where to save this image. Now we can also read an image from the net, and in that case, instead of using file, we can use URL. So let's use now the URL instead of the file. So just before the class, I made a research on the net for fish, and here I just copied the URL equals new URL, and then this is the link of, or the URL of the image. Okay, so this is the name of the image, and here we'll have the URL or the location of the image. Then here im equals inputs or image input output.read, and then you are not reading from the file, but you are reading from the URL, and here we name it u. And that's it. Okay, so here what we did, we read the image from this URL that you created, or you can just use here image input output.read, and here you can use new URL and copy this instead of it. Same on the same design. And then we can display this image. You can select the location. So here we are. This is the dimension or the location of the upper left corner. Okay, so we have a screen. So this is our screen. And here we have where to place your image. If you make here 0, 0, so your image will be here at this position. So here we are talking about the position of the upper left corner. Okay. Now let's run this. So you can see that Java now loaded this image from the net, from the URL that we gave, and we display this image at the location 0, 0. Let's suppose that we want to make the location at, so let's change the location. Let's make it here 200, and for the Y component, let's make it 500. Now we are uploading the same image, and we are displaying the image not at 0, 0, but now at 300 and 500. Okay, we can change it here. We can make 200, 200, 100. So this is the position of the upper left corner. Any question about this? So here what we did, we just used here the first part here, which is to have an image file. We read this file, and we display this file on the screen. Okay, we'll see how to apply some operator and then display the new image on the screen, or save the new image in the desktop or in the arcs. Okay. Now, this program will create a synthetic image, and here we are talking about just blank image. Okay, so here what do we have? We have buffered image BI equals new buffered image, and then here we can see that you are giving the dimension of the image, and here the type of the image here, which is JPEG. Okay, and here we are using graphics 2D GI equal graphics 2D of bi.create graphics. So this is what we have seen in the previous class. So this will add the drawing, and then we can draw this image. So if you draw this image, you can see that we didn't give any data for the image. So we just gave here the dimension 500 by 500, and we didn't give any value for the raster or the data itself. So all the values of the pixel will be zeros. So for the red here, we have 0. For the green, we have zeros, and for the blue, we have also zeros. So here, and all the pixel will be black pixel. Okay. And now, so we already created an image. So we have already the image, and it is an image of zeros. Now we can save this image in a file. So we can here create a file. So file, you give the name of the file equals new file, and then you give the path where you want to save this image. So here I want to save this image in the D, and the name will be here image.jpg. So this is the name, and this is this image. Okay, and then I can use now image input output.write. So I will write what? I will write the buffered image BI that we created here, and the format will be JPEG format. So here we are talking about the compression type. And then the name, so what is here the name of the file? So this is the name of the file, which is initial image. And you can see that here we are making this file writing, so within try catch to prevent generating errors. So if you do this, what you will see, so the draw image will draw this image, and it will be just a black image. And then you can see also that we are saving this image on the D. So if we open the D, we'll find the file here named image.jpg. When we open this file, we'll find also an image that is the black image. So we have already stored. So we are creating here a buffered image, and we are drawing this image, and we are saving this image in the D, and the name will be image.jpg. So you can see that now we have the image. This is our image. So we are creating here an image with a dimension of 100 by 100. Let's create bigger image, 500, 500, and let's draw the image at the locations 0 and 0. I will see bigger image starting from 0 to 0. This is our new image. We can create an image, for example, of the x-axis, let's make it 500, over the y-axis, let's make it just 100. It will be rectangular. And we can display the image. Now you can see that we have the rectangular image. And you also save this image in the computer. So when we go to the D, you will find the file named image.jpg. This is the file. When you open the file, you will see the image that will already be created. Now we can change, can make it 500 by 500. And you can see that now if we open the file, we'll see the new image. So this is the new image, 500 pixel by 500. So now what we did, you have seen how to create sensitive image, just an empty image, a blank image. We have seen how to store an image on the computer. And we have seen how to open an image from the computer. We have seen how to open an image from the link, from the links. Any question about this? Okay, let's continue. Seeing also this is an example of an image. Okay, now we see the image processing techniques. So what are the techniques that we can use here for the image? So the first here type of processing is called spectral rescaling. So here we are making rescaling of the colors. So here, how can we make a rescale of the color? We can use here this formula. So here f of xy will be the color at the position x and y. So I've seen here for every image you have pixels. For every pixel here at the position x and y. So here we have the x position and the y position. So for every value here we have the raster. We have the R, G, and B component. Okay, so what are we doing for these RGB components? We are multiplying the RGB with a factor A. And we can add here also a factor B. So let's suppose that you have here an image and you have the values here 20, 20, 20. So here we have the red, green, and blue. What will be the color of this pixel? Let's suppose that we are talking about one pixel. What will be the color of this pixel? Yalla, try to give an answer. So if you have the same values for red, green, and blue, the pixel will be gray. Okay, and here it will be gray, close to the black or close to the white. I've seen that for the white, we have a value of 255. For the black, here we have a value of 0. So I can see that here we have 20. So here we have something that is close to the black. Now let's suppose that we multiply this value by a factor of 10. I suppose that I will take these values. This is f of xy, okay? And let's suppose that we multiply these values by 10. So what are the new values? The new value will be 200, 200, 200. So the level of gray was here, now it is here. So here we'll see something close to the black, and here we'll see something that is close to the white. So what we did here, we added here some light to the image. So here we are lightening the image. Okay, so if you multiply here the RGB component by a factor that is greater than 1, if your A here greater than 1, that means here what are we doing? We are giving an RGB value that is greater than the original RGB values. So this will make, this will lighten the image. So here we have, we are lightening the image. If the value of A is less than 1, for example, here we take the value of A 0.5. Now 20 multiplied by 0.5 will be 10. Then again here 10, then again we have 10. So you can see that we have something that is close to the black. So what you did here, you darken the image. So if the value of A, is greater than 1, you are lightening the image. If the value of A is less than 1, you are darkening the image. We can also add a value to the RGB color. Let's suppose here, so you can see that here we have A multiplied by f of xy plus B. Okay, so let's suppose that we have here a value of B. Now, if the value of A is 1, so we are not, this will not affect anything. So here, if A is 1, we will find the same image. But here, let's suppose that we have a value of B. Now, let's suppose that the RGB here are, for example, 20, 20, and then we are giving here a value of B, which is, for example, 100. So this will make 20 plus 100, and here we have 20 plus 100, and here we have 20 plus 100. This will give us 120, 120, 120 for every components. So you can select different values. So here I'm just simplifying by making here just same values, but you can have different values. So you can see that here, if the value of B is a positive value, we are adding here a value of 20 plus something. So if you add something, you are lightening the image. And if you use a value of B that is negative value, here you will find something that is close to the 0. Okay, so here we are darkening the image. Okay, any question about this? So we can change here the spectrum. We can make rescaling by changing the value of A and by changing the value of B. Now, if A is 1, B is 0, we'll find the same image. If B is 0, A is, for example, 2, we are lightening the image. If you make the value of A of 0.5, you are darkening the image. Okay, if we take A is 1, B is, for example, 100, we are lightening the image. If A is 1, B is minus 100, you are here darkening the image. Okay, now to do this, we have here in Java what we call the rescale operator. Okay, so here we can create a new rescale operator. So rescale operator Li, so here the name is Li equals a new rescale operator. And here you have to give the value of A, here you have to give the value of B. And here we have no. Okay, so if A here, you can see that here we have A is 2. 2 is greater than 1, that means here we are lightening the image. This is the value of A. Okay, now first of all, we have to create a rescale operator, then you can apply this rescale operator to the image. Okay, so the image here, so you can create here a buffered image. Okay, you have a buffered image, for example, BI, and you have to make BI equals li.filter, and then you can give the source image, and here you can use the other options. Okay, now what is important here is just you have to apply the rescale operator to the image. Okay, once we did this, you can draw the image. Okay, so here we are drawing the image at position 0, and here we are drawing the image at the height of the image. And observe here we are using this, that means we are using the same time. Okay, now we are applying the filter. So we are using here li.filter. This is the source, which is here the buffered image, and then we are using here no. Now in this part, what do we have? Same thing. Here we have rescale operator, dr, for example, equals a new rescale operator. Now the value of A is 0.6. So you can see that 0.6 is less than 1. Less than 1, that means we are darkening the image. Okay, this is the value of B. B here is 0. And then we are applying this filter. So here we are the filter of the source, and then we have null. Okay, and then here we are changing the position so that we can start from this position. Okay, so here for the east component, we have 2 times the width, and for the y component here we have the height of this image. So here the source.get height will give us the height of the image, and the source. So here we have the name of the buffered image dot get width. So the get width will give us the width of the image. Okay, so you can see on the screen here we have the original image, and then here we have lighter image, and here we have darker image. Okay, so here we have just to create the rescale operator, and then you have to apply. You have to filter the image, and then we can draw this image. So let's take the code from here. Let's see part 1, and let's take this code. Now I have 2 buffered image. Now we created, this is the original buffered image IM. So buffered image IM. And here we are reading the parrot, for example, the parrot 2 that is already stored in my computer. We are reading this image and then we are displaying this image. So this will display just the image. And then we'll apply the rescale operator. So here we have rescale operator and I equals new rescale operator. And here we have the value of A, here we have the value of B. So if you make the value of A equals to 1, B equals to 0, this will give us the same image. Then we have to apply this rescale operator to the image by using here the li.filter. So li is the name here of the scale operator. Okay, and then we can draw the image here. We are displaying or we are storing the result of the filtering here in a new buffered image, which is IM2. This is the image IM2. And then we are displaying here the IM2 at another location, choose the location 500 over the X component and 0 over the Y component. Now, if you run, you can see that you have two images. Of the first image and you have the second image, you can see that you have the same, exactly the same image. Why do you have the same image? Because here the value of A is 1, the value of B is 0. Now, if you make the value of A something that is greater than 1, let's make it here 2. We'll find lighter image or darker image. I'm waiting for your answer.
Lighter, because it's
Light.
greater than 1.
Very good. So here we'll find the lighter image. So you can see that now we have two images, and you can see that the second image here is lighter than the first image. Okay. Now, if you want to make darker image, you can select something that is less than 1. Let's make it 0.3, for example. So here 0.3, that means we are multiplying all the RGB component by a factor of 0.3. So this will give us something less than the original value. So it will be darker image. Okay. Now let's take the A as 1 and let's now change the B. If you make value of B here, that is, let's take it 100. We'll find lighter image or darker image.
The same.
Now, let's suppose that we have RGB component. Let's suppose that now for 1 pixel we have R, G, and B. Let's have here 20. Here we have 50. Here we have 100. And then we are applying, this is the value of B, and this is the value of A. Now let's suppose that you are making B equals 100. What does that mean? That means the new image here will be the RGB, or you have f of x, y, which is the RGB component, multiplied by A plus B. So our A here is 1. Okay. Now our RGB component will be multiplied by 1, which is the same value, plus B. So here we have plus 100. So the new image here will be 20 multiplied by 1 plus 100, it will be 120. Then here we have 50 multiplied by 1 plus 100, we have 150. And then here we have 100 times 100 plus 100, it will be 200. So this pixel will be a lighter pixel or darker pixel.
Lighter.
Lighter pixel. So like this.
I thought you were talking about A. So that's why I said same.
Yes, A is, so here we have two parameters, A and B. Okay, we can use both. You can multiply by a factor and you can add here. So I can see that now we have lighter image. So here we added 100 to the RGB component of the pixels. Is clear?
Yes.
Now, if we take a negative value, if we take it to minus 100, what will be the result? That will be darker image. We can use both. We can here make a factor of 0.7, and for the A and minus 100 for the B, it will be also a darker image. Is this clear? So this is called the rescale operator. So first of all, you have to create a rescale operator. Then you have to apply this rescale operator by using here the rescale operator dot filter. And then you can display the image. Just we need 2 lines and 1 line for displaying the image. Okay. Okay, let's see now something else here, which is how to apply geometric transformation to the image. Okay, so this operation has no effect on the pixel intensity. So if you make a rotation, if you make shearing, if you make translation over the X or the Y axis, here we are not applying or we are not affecting the intensities. So the RGB component will be the same, but here we are applying a geometric transformation. Okay. So the program is very simple. So I have to create here a new affine transform. So affine transform X form here. Let's see if we have lighter. Okay, affine transform X form equals new affine transform. And then here we are using, for example, transform of rotation. So X form dot set to rotation. And then here we are using the rotation with an angle of pi over 6. So this is our theta. Okay. Now, to apply this transformation to an image, you have to create what we call a affine transform operation. So here you have OP equals new affine transform operation. So I have to make affine transform OP equals new affine transform OP, and then here you have to use affine transform that you have. Okay, and here for the type here we are using linear type. Okay. So this transformation can be any type of transformation. It can be shearing, it can be rotation, it can be translation, it can be scaling, it can be any type of transformation. Okay, so once we have done, we have to apply this transformation to this image. How to apply? So here we have to use the OP, which is here the affine transform operation dot filter. Okay, and here we are giving the original image. So here the source image here is the image that the original image, and here we have the destination image, and both here they are buffered image. So can test this. So I already prepared it because some here information are missing in the program. So for example, here for the OP. So here we didn't initialize the OP, so I have to make a affine transform OP equals the new affine transform. So you have to add here text here. Okay, and then it will be working. And here you have to load the image, which is the source image, and then you have to prepare also the destination image, which is also a buffered image. So here you have the part 2. Okay, so now we have the buffered image. This is our original image. And then you will have here image 2 and image 3. Image 2 is the image that you have seen previously by applying here the rescale operator. Okay, and then we are drawing here the image. So here we are using just a factor of 1. A is 1. Let's make now A is 2. Let's make it 2. B is 0. And this will display the image 2 at the location 500. So the first code will be same. Okay, now we'll apply the affine transform. Affine transform X form equals new affine transform, and then X form dot set to rotation, and you are using here an angle of pi over 6. Okay, then we have the affine transform operation equals new affine transform operation of X form, and here the type is. Now we have to apply this affine transform to the image. We have to make you have to use here OP dot filter, and the original image is IM, and the destination image is IM3. So we have done. Now we can draw the image. We can use G2 but draw image, And then here we are using where to place the image. So the original image here will be at 0, 0. And then here the image 2, which is an image by using the rescale operator, will be at the location x 500 and y 0. And then we are drawing the third image here at the location. So the third image is the image by using the affine transform of pi over 6. Okay. And then here we are displaying this image at the x position 1000 and at the y position 0. Now let's check what we have. I have 3 images. The first image is the original image. Then here we have the lighter image by applying here the scale or the rescale operator. And then here we have the image by applying the rotation. So instead of rotation, we can have any affine transform. So we can use, for example, set to shear or set to scale. Let's use set to scale. And you have a scale over the x component. Let's make it 2. And let's have a scale. Okay, let's make smaller image. Let's make 0.5, 0.8 for the x component, and 0.8 for the y component. Okay, now let's see what do we have as output. So we can see that we have the smaller image. Then use 0.4, 0.4 over the x and over the y component. You are generating smaller image. This smaller image here, you can save it in the computer by using the image input output dot write, and you can save the new image. You can also save the image 2. So you have 3 images, IM2, and IM3, and you can save each one of these images in the computer. So if I want to change 0x over the, let's make it here 0.5 over the x component, and let's make it 1 over the y component. You see that now we have another image. We have the same y, but for the x, we have x divided by 2. Okay, we can use, for example, here, let's make 1.5 over the x component and 1 for the y component. You can see that you have a larger image. You can apply, for example, shearing. Let's use here instead of set to scale, let's use set to shear. Let's make shearing over the x axis, let's make it 0.5. And over the y axis, let's make it 0. And then you can see that we have shearing image. Okay. You can have, for example, -1 here and 0. Have another type of shear. Now, if you use here set to scale and use -1 and 1, what will be the output? So I've seen this in the midterm. So how to make the mirror. So we can use here set to scale, and for the x component, you can set it in x component of -1. And for the y, you can make it as 1. You can use set to translation, set to rotation, any type of sign transform you can. Any question? Okay, now we'll see another part, which is the image filtering. Image filtering is very, very interesting. Here we'll apply a filter for the image. Okay, and we'll apply this filter pixel by pixel. So the image filtering here intended to especially يعني you are working on the pixels, especially enhance the image properties like the edges. We can extract the edges from the image. Okay, so the main purposes of filtering are noise detection. We'll see how to detect or how to reduce the noise. Okay, how to make the edge detection, and how to make the image sharpening, etc. So here we are using the convolution. So the convolution is an operator that you have in math. Okay, so the convolution generally we have two matrices, and here we have the convolution product of these two matrices. So how does it work? So we have a kernel. Now in this example here, we have an image. Okay, and we have many pixels. Let's suppose that we want to check the new value of this pixel. So here we have any values for the R, G, and B component. Okay. And then we have a kernel here. We have a filter. So the filter can be, for example, 3 by 3 matrix, or 4 by or 5 by 5 matrix, or 7 by 7 matrix. So this is called the kernel. So you have an example of kernel 3 by 3 kernel. So here, what are we making here? We are multiplying. So we will apply this kernel to all the pixels. What does this mean? Now let's suppose that this is our image, and we want to find the new value of this pixel. So how to apply this filter here? It's like here we will take this filter and we will make this filter here. Okay, so now what is the new value here? The new value will be the value of the pixel will be multiplied by 1 plus the value of this neighbor multiplied by 1 plus the value of this neighbor multiplied by 1 plus the value of this neighbor multiplied by 1 plus this neighbor plus this neighbor plus this neighbor plus this neighbor plus this neighbor. And here when you add these values, you will find here 9, and you want to keep the same ratio, so you can divide here by 9. So what we did here for this pixel, we took the average of all the neighbors' pixel, including the original pixel. So if you take the average, so for every pixel, we are taking the average of all the neighbors of this pixel. So here it is called smoothing filter. Okay, so here it depends on the filter that you are applying. So we have some filters that make smoothing. We have some filters that, so here you can see that you have original image like this. If you apply smoothing filter, you can see something that is smooth like this. So for every pixel, we are taking the average. So the smoothing here is used to remove the noise. So for certain type of noise, for example, here if you have white noise, or also paper salt noise. So here, generally, if you are using the smoothing will remove the noise. So let's see this filter here. So here we have another filter, and here you can see that how to apply. This filter will be applied for all the pixels. Okay, it will be applied for this pixel, then this pixel, then this pixel. This is what this means, the convolutional product. Okay, now if you have a pixel like this, you can apply this kernel here. Okay, so what is the new value of this pixel? It will be the value of this pixel multiplied by -1 plus the value of this pixel multiplied by -1 plus the value of this pixel multiplied by -1 plus the value of this pixel multiplied by -1 plus the value of the original pixel here multiplied by 4. Okay, so here you can see that the addition or the sum of the values that we have here equals to 0. So if the sum is 0, here it means we are removing the column. So here, what are we making here? This is a filter that detects the edge. So here we call this a derivative. So what does mean derivative? So the derivative here, we are taking the pixel to the right minus the original pixel, the pixel to the left minus the original pixel. So here we are detecting here the edges of the image. Okay. Here we have almost the same, but instead of 4 here we have 5. But if you add here the values, if you add here -1 plus -1 plus -1 plus -1 plus 5, you find 1, not 0. So 1, that means we will have the colors. And in addition to the color here, we are extracting the edges. So this will give us sharper image. We have the image, and you are accentuating here the edges. You are extracting the edges, and you are adding the edges to this image. Okay, so let's see how does it work. So first of all, we have to create this. This is a matrix. This is an array. So here we have floats, and we have an array of floats, and the values here we can use any value of float. Okay, and how to write? What is the order? We have to make now this element, then this element, then this element, then this one, this one, this one, and finally this one, this one, and this one. So the order here of filling will be this. Will be number 1, 2, 3. And 4, 5, 6, and 7, 8, and 9. Now you can see the first element here will be 0. So we have 0f, and we have -1. We have 0, then we have -1, then we have 4, then we have -1, then we have 0, -1, and then we have again 0. Now what we did, we created just an array of float. Now we have to convert this array of float to a kernel. So we have to create a new kernel, and then it is a kernel of 3 by 3. So this is 3 by 3 kernel. Okay, and you are applying this kernel to the array that you already created. Okay, now we have to create a convolutional operator. Okay, so here we have to make convolutional operator here. OP equals the new convolutional operator of the kernel that you have already created, and then you have to apply this kernel by using here op.filter, and you have to apply this to the image in the source image. Okay, so let's take this part from here. Let's remove the rescale operator. Let's remove the affine, transform. We don't need them. So this is the original image. Now let's create the convolutional operator. Here you have the image 2. Now this is the array. So you have 0, -1, 0, -1, 5. So what is this kernel here? So you can see that here, let's use the 10. So the first value is 0, then we have -1, then 0. So here 0, -1, 0. And then we have -1, 5, -1. And then we have 0, -1, 0. So this is the kernel that we are using. So this kernel will sharpen the image. Okay, we make sharper image. And let's apply this image of this kernel to the parent that we have. So we have to create a kernel. So it is 3 by 3 kernel of this array. And then we have to create a convolutional operator. If we 2 equals new convolutional operator of this kernel. Then we have to apply this kernel to the image. And we are showing here on IM2 image 3, which is the filtering of IM. And IM2 here is the buffered image. And then we have to draw this image, which is IM2. At, for example, here, let's use 500 for the X component and 0 for the Y component. So now this will draw the original image at the position 0, 0, and then the filtered image at the position 500, 0. So what can you see here? Let's start with the value here, 4, so that you can understand what we're doing. So the 4 is this kernel here of 0, -1, 0, -1, 4, -1, then 0, -1, 0. Now, if the addition here gives you the value 0, you will find here an image without color. So you are just extracting the edges. Okay, so this filter will just extract the edges. So what can you see here? We have the edges of the image. Okay, so you can search on the net for additional kernels. Okay, on Google you can type kernel for example, we can extract only the horizontal edges. You can extract only the vertical edges. Okay, so we can apply. You can have many filters. Okay, so on Google we can use here kernel filter for horizontal edge detection. So here you can see that this filter will detect the horizontal edges. So this filter will detect the vertical edges. Okay, so let's try this one. Okay, so here we have 1, 1, 1, then 0, 0, 0, then minus 1, minus 1, minus 1. So you can see that the addition here is 0. Okay, so we'll find here only the vertical edges. Okay, let's try this. So you can see that here we are detecting all the edges. But let's try the new filter. So we'll have 1, 1, 1. And then we have 0, 0, 0. And then we have minus 1. Have minus 1. And you have also minus 1. Now let's run this. So you can see that here we are trying to see the horizontal edges. Yeah, and you are more giving the horizontal edges. Okay, now if you try to extract the vertical edges, so for the vertical edges, we can use this filter. 1, 0, minus 1, 1, 0, minus 1, 1, 0, minus 1. Let's try this. 1, 0, minus 1. Then again 1, 0, minus 1. And then again 1, 0, minus 1. So let's check this image. So you can see that you are seeing more the horizontal edges. Now, you can see that now we have more the vertical edges. So you can see that here it's like we are accentuating here these vertical edges. So you can see that more here the vertical edges. If you return back to the original filter, so the original filter that we used will detect both the vertical and the horizontal edges. Any question about this? Okay, let's continue. So here you can use any kernel. You can have 3 by 3 kernel, you can have 5 by 5 kernel, you can have 7 by 7 kernel. So it depends on the kernel that you are using. And this kernel will be executed for all the pixels, one by one. It is here convolution product. So it is called math convolution product. So if you return back to the program, if you make the center pixel equals to 1, what we have as the result here, you can see that we have the image, the original image, and here we are trying to find the vertical edges in addition to the image. We are sharpening here the vertical edges. Now for the color space here, we can, we have seen that for the pixels, we can have the raster, which is the values of the pixel, the RGB of the grayscale image. And you have here the color space. Okay, so the color space here will make the mapping between the values and the color that you are displaying. So we can have here gray color space. We can have, for example, RGB color space or sRGB for standard RGB color space. We can have linear RGB color space. Okay, so let's see how to change an image. So this is the image of Lina. Okay, and let's see how to change this image to grayscale image. Okay, so here we are creating a new color space. So color space CS equals color space dot get instance color space dot gray here, CS underscore gray. So we are taking here the characteristics of the color space gray, and then here we have to apply this color space. So color convert operator. So to change the color space, we have to use the color convert operator equals a new convert color operator, and then you have the CS, and then you have the null, and finally you have to apply this to the image. Okay, and then we can display the image. So to do this, we can change the image from color image to grayscale image. Now, let's remove this. Now we have the original image, and then now let's use the color space. Let's add the library for the color space. So color space is equals color space dot get instance, and here we are taking the instance of the gray, and then color convert operation of the new convert operation of CS color space, and then here the image 2 IM2. We have to apply now this color space to the image IM. Now our image is IM, and we are applying this new color space to the image IM, and we are saving this to the IM2, which is also a buffered image. Okay, now we can draw this image. So G2.draw image, and we want to do IM2. Let's use now at the location 500 for the pix. 0 for 1. Now you can see that the first image is a color image, and the second image here is a grayscale image. So applied here the grayscale color space to the image IM, and we store this in the image IM2. So you can see that after making any transformation or any modification, you have to apply the modification by using here the field. Okay, any question about this? No questions? So the last part here will be just changing here the lookup operation. So here we have an example of lookup operation. So here we are creating just an array. Okay, so it is an array of short, that means we have 8 bits to write the values. So we have the values from 0 to 255. So this is the type short. So we have an array of short with a length of 256, and here we are storing the values from 0 till 255. But here we are creating a loop. So for short I equals to 0, I less than 256, I plus plus. Data of I will be 255 minus I. So it's like here we are applying an inversion of the color. So if you have a value of the color, for example, of 20, and so it's like here the negative of the image, or the inverted or reversed color of the image. So if you have RGB component of, for example, here 100, here 150, and here 200. So it is the negative or the inverse of this image. So if you make 255 minus 100, We find here 155 for the rent. And here we have to make 255 minus 150. So this will give us here the new value 105, for example. Okay, and then same thing here, we have to make 255 minus 200. You will find here 5. So this is the red, this is the green, this is the blue. So if you apply this operation for all the pixels, here you are inverting the colors of the image. So here you have an example. So here you are creating an array, okay, and this is the length of the array, and you are filling this array by the values of 255 minus. And at the beginning, I is 0. The first value of the array here will be 255 minus 0, so the first value will be 255. And the second value, I will be 1. We have 255 minus 1, it will be 254. Then here we have 253. Then we have 252, etc. So the last value will be 255 minus 255 will be 0. Then we can create a lookup table. So lookup tables, here we are giving the name because a new short lookup table. And here we are applying this lookup table for this array, which is the data. Okay. And then here we have the lookup operation of because new lookup operation of this lookup table. And then same thing, you have to apply this lookup table by using here op.filter, and you are saving the result to the destination image. So you have an example of. Any question about this? So we have done for today's class. Do you have any question?
No, thank you, Doctor.
Okay.